Hi, this is the first topic in our discussion of counting. It's called the fundamental principle of counting. Its statement formally is if we have a bunch of independent events, E1 all the way to En, then the total number of possible combinations of outcomes is the product of the numbers and outcomes of each event. So that sounds complicated, but actually it's kind of simple. So here's like a trivial example from it. So how many possibilities are there if you flip a coin and roll a dice? You have your independent events, so E1 is flip a coin, and E2 is roll a dice. So the total number of possibilities is, there's 2 possibilities for flipping a coin, 6 possibilities for rolling a dice, and you have 12. So now, independent events, they're not just events. They can be much more like a variety of things. So our next example is how many passcodes? So passcodes are 3 digits from 0 to 9. Have no 3. So in our case, we just have one passcode. So we don't actually have events. But we can pretend like we have events. So our events could be our first digit, our second digit, and our third digit. So each of these don't depend on the other. So what we can do is we have 9 choices for our first digit, 9 choices for our second digit, and 9 for our third. And we can have 729 different passcodes. Alright, that's not so bad. So we'll go on to our next example. So this has a little bit of mix of number theory along with it. So how many positive cubes divide 3 factorial times 5 factorial times 7 factorial? Alright, so this is not directly counting. So we should consider what cubes mean. So if you have a cube, then what we know about it is that it's prime factorization, right? So all of these exponents are divisible by 3. So we note that if we have a divisor of this, so say we have a divisor, we just need to choose exponents for 2, 3, 5, and 7 because that's the only primes that are there. We just need to choose exponents that have that are multiple of 3 and are less than the number of factors in this. So what is the prime factorization of this? Well, you can expand this. I can demonstrate it. You can expand this as 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1 times 7 times 6 times 5 times 4 times 2 times 1. So how many factors is this? Well, for 2's we have 1 over here, additional 2, additional 1, additional 1, additional 2, and additional 1. And if you count them up, you should get 8. For 3's we have something over here, a factor of 3 over here, a factor over here, and a factor over here. 4's. 5's we have 2, and 7 we have 1. So our divisor the exponents have to be less than divisible by 3. For E1, this can be 0, 3, or 6. Right? For E2, it can be 0 or 3. For E3, it can be only 0, and so will E4. How many possible combinations? 3 times 2 times 1 times 1. That's 6. And these are just a few examples, and you can use this versatility and different problems.